All right, chemistry. This is the first part of your video lecture for Chapter 5. We're going to start talking about the periodic table and really trying to hammer down on how to use the periodic table to get information. Right? Now, remember, you'll always have access to a periodic table. You always have access to it. You should always have it out whenever you're working on any type of problem. To not have your periodic table out would be considered stupid. Okay. Also, I hear what you guys say in class, and I know that you love it when we combine two sections at once, and so we're going to do that right now. So, we're going to combine sections 1 and 2. So we're going to start with the history of the periodic table. So after this portion of the video lecture, I want you to be able to explain the roles of Mendeleev and Moseley in the development of the periodic table. I want you to be able to describe the modern periodic table, explain how the periodic law can be used to predict the physical and chemical properties of elements, and then describe how the elements belonging to a group of the periodic table are interrelated in terms of atomic number. So we're looking for patterns here. You don't necessarily have to wrap your head around exactly why the patterns are the way they are. Simply start with recognizing the patterns. Pure elements at room temperature and atmospheric pressure can be either solids, liquids, or gases, right? Those are the three common states of elements on our planet. Some elements are colorless, some are colored. Despite the differences between elements, groups of elements share certain properties. Like we were talking about in Chapter 4 with electron configurations, especially those what are called valence electrons, those outer electrons, the electrons in the highest occupied energy level. They are the same for any element in the same group, in the same vertical column. Because of that, because they have the same number of valence electrons, they have the same properties, right? They share certain chemical properties. For example, the elements lithium, sodium, potassium, rubidium, and cesium can combine with chlorine, for example, at a 1-to-1 ratio. So they'll form lithium chloride, sodium chloride, potassium chloride, rubidium chloride, and cesium chloride. Notice how they're all combining at a 1-to-1 ratio. One atom of the group 1 element and one atom of chlorine. All of these compounds are white solids that dissolve in water to form solutions that conduct electricity. They all have the same type of characteristic. The elements fluorine, chlorine, bromine, and iodine can combine with sodium, for example, also at a 1-to-1 ratio. They'll form sodium fluoride, sodium chloride, sodium bromide, and sodium iodide. All of these compounds are also white solids that can dissolve in water to form solutions that conduct electricity. And so we see that when we deal with elements in the same group, they have similar characteristics.
All elements are organized by their properties on the periodic table. All elements are denoted by 1, 2, or 3-letter symbols. The first letter of the symbol is always capitalized.
Again, let's keep looking for patterns. In 1865, the English chemist John Newlands arranged the known elements, because not very many were known at that time, the known elements according to their properties and in order of increasing atomic mass. We'll see that we actually don't organize our periodic table in terms of increasing atomic mass anymore, but there was no way for John Newlands to know why we would do that. So they simply arranged them by increasing atomic mass. And he placed the elements in a table. Newlands noticed that all of the elements in a given row had similar chemical and physical properties. Because these properties seem to repeat every 8 elements, Newlands called this pattern the law of octaves. Octaves, right? Referring to 8. Law of octaves. In 1869, the Russian chemist Dmitry Mendeleev used Newlands' observation and other information to produce the first orderly arrangement or periodic table. Periodic means happens in periods, regular repeating systems, of all of the 63 elements known at that time. Mendeleev wrote the symbol for each element along with the physical and chemical properties and the relative atomic mass of that element on a card, and that's how he arranged his table. He wrote everything down on cards and simply manipulated them in three-dimensional space until he found the pattern that made the most sense. But like Newlands, Mendeleev arranged the elements in order of increasing atomic mass. Mendeleev started a new row, right? Those horizontal periods, a new row. Each time he noticed that the chemical properties of the elements repeated. He placed elements in the new row directly below elements of similar chemical properties. Remember, he had no understanding of valence electrons per se, and so he wasn't counting the number of valence electrons. He was simply going by the understood chemical properties of each element. Mendeleev made two interesting observations. Mendeleev's table contained gaps that elements with particular properties should fill, but there was no element with that known set of properties. Mendeleev predicted the properties of these missing elements, right? And so essentially what he did is he said that there is an element that exists that would go right here on the periodic table, but no one's discovered it yet. And he actually predicted the properties, and he actually ended up naming those. It's actually kind of interesting what happened. The other thing that he noticed is that the elements do not always fit neatly in order of atomic mass. There are actually a few different examples of elements when they are arranged according to their properties actually broke that increasing atomic mass rule. The example that he noticed was tellurium and iodine. So as Newlands always placed them in terms of increasing atomic mass, this actually broke that pattern with tellurium and iodine. And you'll notice that they actually don't go by increasing mass for those two elements. So this is an example of some of the elements that Mendeleev predicted would exist that were completely unknown at the time, and he actually gave them names up at the top. For example, he predicted that gallium existed, and he actually predicted that it would have a density of 6. When it was actually discovered and observed later, it had a density of almost exactly 6. He anticipated how it would bond with oxygen, and he was right. What we now know known as scandium, he predicted the density perfectly. He also anticipated how it would form an oxide. He also predicted that it would dissolve in acid, and yes, it did. And then germanium, again, he predicted the density very accurately. He anticipated the melting point. He anticipated how it would form an oxide. He anticipated the density of that oxide, the formula of a chloride, and then he also did a decent job of anticipating the color. And so just by looking at the repeating characteristics in the periodic table, he was actually able to make these predictions. Now, about 40 years after Mendeleev published his periodic table, which was actually just in a textbook, and it wasn't like a big discovery blown out of proportion, an English chemist named Henry Moseley found a different physical basis for the arrangement of elements, right? So not according to atomic mass. Moseley studied the lines in the X-ray spectra of 38 different elements, and he found that the wavelengths of the lines in the spectra decreased in a regular manner as atomic mass increased. When the elements were arranged in increasing atomic number, right, which we now know is the number of protons, the discrepancies in Mendeleev's table disappeared, meaning they were super consistent with each other. And so realize before this time, the periodic table was arranged in terms of increasing atomic mass because there was no technique, there was no device that could determine how many protons were in the nucleus. Remember, up to this point, we simply knew that the nucleus was positively charged, and that's it. There was no way to count the number of protons. And so Moseley, with his X-ray crystal diffraction method, was able to count the atomic number, the number of protons. And this became the basis for ordering the periodic table. And so, like that backwards little thing with tellurium and iodine, the reason that the atomic masses were backwards was completely explained because of the atomic number. So Moseley's work led to both the modern definition of the atomic number and showed that atomic number, not atomic mass, is the basis for the organization of the periodic table. So now we're going to talk about the periodic law, which is part of one of your objectives. Mendeleev's principle of chemical periodicity is known as the periodic law, which states that when the elements are arranged according to their atomic numbers, elements with similar properties appear at regular intervals, right? And so this builds into how we organize the periodic table. Elements in each vertical column, right, which we call a group of the periodic table, have the same number of electrons in their outermost energy level. Hopefully you remember that from last chapter. The electrons in that outer shell are called valence electrons. Valence electrons are found in the outermost shell of an atom, and that determines the atom's chemical properties, meaning the number of valence electrons determines the atom's chemical properties. Hopefully you remember that elements in the same column, the same group, have the same number of valence electrons. So if they have the same number of valence electrons, they should have the same types of properties. This is an explanation of why that is the case. Elements with the same number of valence electrons tend to react in very similar ways. It's because the S and P electrons, right, electrons in the S sublevel and in the P sublevel, they fill sequentially. The number of valence electrons in the S and P block elements are very predictable. And so this is a graphic that I've included in your notes, and I really want you to get used to this pattern. Hopefully you remember this from chapter 4 when we did electron configurations, but is a quick reminder. Notice the pattern in the S block, right, on the left side of the periodic table, and in the P block over here on the right side. Notice that the electrons fill very predictably because it's just a straight up sequence. 1 and 2, 1, 2, 3, 4, 5, 6. 1 and 2, 1, 2, 3, 4, 5, 6. And as you go down any particular column, like here with the halogens, these are always P5, 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 P5. And so they have the same number of valence electrons, therefore they'll have the same types of characteristics. So a vertical column in the periodic table is called a group. We've already mentioned that. And elements in a group tend to share chemical properties because they have the same number of valence electrons. A horizontal row on the periodic table is called a period, like we've already noted. Elements in the same period have the same number of occupied energy levels because they're all in the same main energy level, right? The N value, the principal quantum number. For example, all elements in period 2 have atoms whose electrons occupy 2 principal energy levels, including N is equal to 1 and N is equal to 2, and they all have electrons, or they may or may not have electrons in the 2s or 2p orbitals. So the periodic law is alive and well and stated on most periodic tables. This is the type of information that you can get from the periodic table. You can get the atomic number, the symbol, the name, average atomic mass, and electron configuration. Now, not all periodic tables have all of this information. For example, the periodic table that I want you to have and you to use does not have the electron configuration because I want you to recognize the pattern yourself and practice yourself.
There are 92 naturally occurring chemical elements, or atoms. They differ in the numbers of protons, neutrons, and electrons they contain. The periodic table arranges these elements in order of complexity. For example, hydrogen, element 1, is the simplest atom because it contains only 1 electron and 1 proton. It appears at the top left of the table. Unquadium, at the other end of the table, is the most complex, with 114 protons and 114 electrons. The number of protons in an atom is the same as its atomic number. The atomic number for each element appears just above its letter abbreviation. The periodic table also arranges elements together in groups, or families. Elements in a vertical column are called a group. The elements in a group have similar chemical properties. For example, the noble gases on the rightmost edge of the periodic table have great stability and limited reactivity with other elements. Group 1, the alkali metals, have similar reactivity. They readily form hydrogen gas when added to water. A horizontal row of elements forms a period. The differences between elements in a period and elements in the next period are consistent between the groups. For example, if we look at the difference between elements in group 18 and in group 1, we see that the difference in atomic numbers is constant. 8, then 8, then 18, then 18, and then 32. This means that the atoms are consistently becoming larger by a set number of protons as you move from period to period. Note that there is a special block of elements below the main table known as the lanthanide and actinide series of elements. They are grouped together and placed below the main body of the table to keep it from becoming too wide. Elements with atomic numbers greater than 92 do not occur naturally, but can be produced in laboratories. Most are not very stable and decay rapidly.
So let's start talking about our modern periodic table. By the way, Mendeleev, again, did not have access to all of the elements that we now know exist. One of the reasons is he simply didn't have the devices to do it. That technology did not exist. Again, there are three types of elements that he was completely unaware of. The first type are the lanthanides, because they weren't described until the early 1900s. Elements from curium, number 58, all the way up to number 71, are separated and identified, right? So when Mendeleev was doing his work, these were not described yet, so he had no reason to throw these into his periodic table. Also known as the rare earth metals, right? It's another name for this group. Account for less than 0.01% of naturally occurring elements. The other type of element that he was completely unaware of is the actinides. These, for the most part, need to be synthesized, right? The first three don't. The first three occur naturally, but anything beyond 92 has to be synthesized. So these are numbers 90 through 103. Both of these groups were pulled out of the periodic table for space reasons. Okay, it would simply be too large to actually print on one piece of paper, right? So we have the S block over here on the left. We have the P block on the right. We have the D block in the middle, the transition metals, and then we have the F block with the lanthanides and actinides pulled out of the periodic table because they would simply be too long. If the lanthanides and actinides were not pulled out of the periodic table, it would look like this. And I hope you can see that this is a pretty long piece of paper, and it's simply awkward. The last group that Mendeleev was completely unaware of was the noble gases. In 1894, argon was discovered. During this time, elements were studied through their reactivity with other elements. And even though these noble gases are constantly present in the atmosphere, argon, one of the noble gases, is so chemically unreactive that it escaped notice because that's the only way that you could discover or study an element, is how it reacted. So if these elements don't react, they were unknown. Argon was the first noble gas to be discovered. And so we want to, again, hit this idea of periodicity because we're talking about the periodic table. So periodicity refers to the fact that elements with similar properties are found at regular intervals, right? Regular intervals within the periodic table. That's what it means to be periodic. So hopefully right now you can explain the roles of Mendeleev and Moseley in the development of the periodic table, describe the modern periodic table, explain how the periodic law can be used to predict the physical and chemical properties of elements, and describe how the elements belonging to a group of the periodic table are interrelated in terms of atomic number. Now I said we're combining sections, so here's section 2. Describe the relationship between electrons in sublevels and the length of each period of the periodic table. Locate and name the 4 blocks of the periodic table and explain the reasons for these names. Discuss the relationship between group configurations and group numbers. And then describe the locations in the periodic table and general properties of the alkali metals, the alkaline earth metals, the halogens, and the noble gases. So let's start with the main group elements. Elements in groups 1, 2, and 13 through 18 are known as the main group elements, main group elements. Main group elements are in the S and P blocks in the periodic table. The electron configurations of the elements in each main group are regular and consistent. The elements in each group have the same number of valence electrons. That's not new. That is from a couple of sections ago, right? Elements in each group, as long as they're in the same group, they have the same number of valence electrons and therefore the same types of properties. The main group elements are sometimes called the representative elements because they have a wide range of properties. At room temperature and atmospheric pressure, many are solids, while others are liquids or gases. About half of the main group elements are metals, and many are extremely reactive, while several are completely non-reactive. The main group elements, silicon and oxygen, account for about 4 in every 5 atoms found on or near Earth's surface, because they make up rocks, right? Silicate minerals are made up of silicon and oxygen, right? And SiO4 configuration, I believe. Don't quote me on that. It's been a while since I've gone through that stuff. 4 groups within the main group elements have special names. And in fact, there are more names than this, but they're just not quite as well known, and you're not required to know them for this course. These groups are in group 1. They're called the alkali metals. There's group 2, the alkaline earth metals. There's group 17, known as the halogens, and then there's group 18, the noble gases. So here's a diagram or a graphic representing the main groups. They're highlighted here in blue, right? And they are on the left and right side of the periodic table. So this is the S block, and this is the P block. And so the D block elements as well as the F block elements are not considered to be part of the main group elements, the representative elements. So the alkali metals make up group 1, right? They're called alkali metals. So that's lithium, sodium, potassium, rubidium, cesium, and francium. Alkali metals are so named because they are metals that react with water to make alkaline solutions, right? Basic solutions. Because the alkali metals have a single valence electron, they are very reactive. They're very reactive. Because in losing its one valence electron, potassium, for example, achieves a stable electron configuration. Alkali metals are never found in nature as pure elements. Never. They're always found in compounds. Why? Because they're so reactive, because they only have one valence electron. They're so reactive that by the time we observe them, they've reacted with something else to form a compound. And so as we look through the alkali earth metals, we see that they have very, somewhat similar characteristics. So we have lithium, sodium, potassium, rubidium, and cesium. The alkaline earth metals make up group 2. Group 2 elements are called the alkaline earth metals. Alkaline, not alkali anymore, alkaline earth metals. They are slightly less reactive than the alkali metals, but again, they are usually found as compounds. The alkaline earth metals have 2 valence electrons and must lose both of their valence electrons to get to a stable electron configuration. It takes more energy to lose 2 electrons than it takes to lose 1, right? And so it takes more, right? It takes more for the alkaline earth metals to lose 2 because it takes more to lose 2, so it takes more energy to lose 2, and so they're less reactive. It takes more energy for them to actually accomplish that task, to lose both valence electrons to get to that stable electron configuration. The halogens in group 17 are also very highly reactive. They are the most reactive group of non-metal elements. When the halogens react, they often gain the 1 electron needed to have a full 8 valence electrons, right, to satisfy that octet rule, and to have a completely filled outer energy level, which, by the way, is known as a noble gas electron configuration, because there's that full octet. Because the alkali metals have 1 valence electrons, they are ideally suited to react with the halogens, which want to gain 1 valence electrons. So whenever there is a halogen that reacts with a metal, we call it a salt, right? When a halogen reacts with a metal, we call it a salt, or at least most metals. Group 18 elements are called the noble gases. The noble gas atoms have a full set of electrons in their outermost energy level. They satisfy the octet rule. They have the full 8. They're said to have a noble gas electron configuration. The low reactivity of the noble gases leads to some special uses. The noble gases were once called the inert gases because they were thought to be completely unreactive. But in 1962, chemists were able to get xenon to react, making a compound that was pretty convoluted and actually took a lot of work. And then in 1979, chemists were able to form the first xenon-carbon bonds. Now, just because they could make it happen doesn't mean it happens naturally. You can create bonds, but they certainly don't happen in nature with noble gases. Hydrogen is actually in a class all by itself, right? It is in group 1, but we certainly don't call it an alkali metal. Hydrogen is the most common element in our universe, okay, by far. It is estimated about 3 out of every 4 atoms in our universe is hydrogen. Because it consists of just 1 proton and 1 electron, hydrogen behaves unlike any other element. Hydrogen is therefore in a class by itself on the periodic table. With its 1 electron, hydrogen can react with many elements, including oxygen. The majority of elements, including many main group ones, are metals. There are lots and lots of metals on the periodic table. Metals are recognized by their shiny appearance, but some non-metals, metal elements, plastics, and minerals are also shiny, right? So just because something is shiny doesn't automatically mean it is a metal. And so in blue here, we have all the different types of metals. So on the periodic table, you can see that most of the elements are in fact metals, with a couple of these non-metals over here on the extreme sides. So we talk about metals as a group because they share many properties. All metals are excellent conductors of electricity. Electrical conductivity is one property that distinguishes metals from the non-metal elements. Some metals, like manganese, are very, very brittle, however. Other metals, such as gold and copper, are ductile and malleable. When I say ductile, it means that the metal can be squeezed out into a wire, right? It can be drawn out into a wire. When I say it's malleable, it means that the metal can be hammered or rolled into sheets without breaking. It simply smooths or flattens into a sheet.
The malleability and ductility of metals are possible because metallic bonding is the same in all directions throughout the solid. When a piece of metal is hammered, one plane of atoms in a metal can slide past another without encountering any resistance or breaking any bonds. When a piece of metal is drawn or squeezed, the atoms slide past each other without breaking bonds. This ability of metals to be shaped by hammering or drawing is the basis for much of the technology that we use in our daily lives.
So within the metals, we have transition metals, and transition metals constitute groups 3 through 12. Remember that these are the groups that were kind of excluded when we talked about the main group elements. So groups 3 through 12 are called the transition metals, and they're sometimes called the D block elements because of their position on the periodic table. They're in the D block. A transition metal is one of the metals that can use the inner shell before using the outer shell to bond, meaning when we typically say that is the valence electrons that bond with other atoms, the transition metals actually have the capacity to use their inner shell electrons, the D level electrons, to form more bonds, right? And so they're a little bit unique in that sense. Now, a transition metal, for our purposes, is very unique because it may lose 1, 2, or even 3 valence electrons, depending on the element with which it reacts, as opposed to simply satisfying an octet rule like the main group elements do. Generally, the transition metals are less reactive than the alkali metals and the alkaline earth metals are, but some transition metals are so unreactive that they seldom form compounds with other elements at all. Now let's talk about the f orbitals here. The elements in the first of these rows, right, is called the lanthanides because their atomic numbers follow the element lanthanum. A lanthanide is a member of the rare earth series of elements whose atomic numbers range from 58 all the way to 71. Elements below the lanthanides are called actinides because they follow actinium. An actinide is any of the elements in the actinide series which have atomic numbers from 89 all the way to 103. As one moves from left to right along these two rows, electrons are added to the 4 f orbitals in the lanthanides and to the 5 f orbitals in the actinides. The lanthanides and actinides are sometimes called the F block in the periodic table. The actinides are unique in that their nuclear structures are more important than their electron configurations. Because the nuclei of actinides are unstable and spontaneously break apart, all actinides are highly radioactive. We're still talking about metals. Another property of metals is the ability of metals to form alloys. An alloy is a solid or liquid, right? So even like a sword made of steel, that steel is an alloy. So it can be solid or liquid mixture of two or more metals. The properties of the alloy are different from the properties of the individual elements. Often these properties eliminate some disadvantages of the pure metal. A common alloy is brass. It's a mixture of zinc and copper. Brass is harder than copper and more resistant to corrosion, and so that's where its value lies.
Elements can frequently be described as being metals, nonmetals, or metalloids. Metals are good conductors of heat and electricity. They are often shiny and bend easily, like this wire. Nonmetals are poor conductors of heat and electricity. They frequently have a dull appearance and break easily rather than bend. Metalloids have some characteristics of metals and some characteristics of nonmetals. If the temperature is high enough, they will conduct electricity similar to a metal, but no electricity is conducted at room temperature. They are more brittle than metals, yet easier to bend and form than nonmetals.
So that'll do it for this video lecture. I will see you next period.